Okay. So we left from here, right? The explaining the OpenGL code. So I will quickly revise from the beginning and then go ahead.
So your screen is not shared, I think.
Ah, sorry. I'm so sorry. Wait. Wait. Okay. Can you see it now?
Yes.
Okay. Thank you. I totally forgot to do this. Okay. Uh, so we started with the basic skeleton of OpenGL code. As I mentioned, this GL glad.h is, of course, it's the library you include, and then in the main function. So we start with the glad init function. So init function, what it does is that it initializes the glad library and negotiate a session with the windowing system. So that means it might happen that your windowing system, like it doesn't have a proper support, and OpenGL cannot connect to the Windows system. So in that case, glad init will initiate a failure message, and the program will terminate. So this glad init is the most important thing. So start a program with glad applications. So and then basically you select the display mode. So in the display mode there are different parameters. So they are basically combined together as different arguments. So here I have written in here it's a glad single. So it means it's a single buffered window. So sometimes what happens, we have only a single display. So let's say you are displaying a colored rectangle or something. So then you use glad single and there is no problem with this. But sometimes what happens, we have animation. So animation means we have double or triple or other buffers. So in this case, what happened? Let's consider two buffers. So with the two buffers, so what happens? So let's say this is buffer one and buffer two. So this is visible and this one is not visible. So what happens? We render the frame or render the buffer that is not visible. So that means we'll render B2 and then basically disable B1 and then keep B2 to the display. So that means we are switching the buffer every time basically. So that means so each frame the role of the two buffer would get reversed. So and this reversing process continues until the program gets terminated. Okay. And when you use single buffer window, sometimes you will see to use GL flush to flush everything to the output screen. And when you have double buffer window, then you use the swap buffers, because then the swap buffer actually does the switching between the buffers in between animation or the rendering process. Okay. And glad RGB is just a color property. You can use other color models also, but RGB is pretty standard, and we use glad RGB most of the time. You also have to specify the window size, and so here we have specified 500 cross 500. So it's the width and the height, and also the window position at 00. So all these things has to be initialized by the windowing system. So you have to do it specifically by saying this. So there is no default value. Well, the default value is like a -1 but you have to specify an exact value. So -1 is not acceptable. And then you create a window with the glad create window and just name the window like it's called it simple. So it just opens the window and runs it. Okay. So then comes this display function, display callback. So this is one of the most important thing in OpenGL. So this display glad display func basically it sets the display callback for the current window. So that means what is a callback? So callback is a function so in which the library like glad calls it when it needs to know how to process something. So that means you are pressing a keyboard or you are clicking a mouse or something. So what will happen after this click? So that will be specified here actually within this glad display function. And your glad program needs to know what to do with this. So this will be called basically when there is a need to do something. So when something happens, basically this will be called. So when something happens means it can be like a window resize or redraw command, or user is giving some input, or there is some animation. Okay. So this my display, this function, as I mentioned in the previous day, I think somewhere here. Yes. So basically this is a pointer to a function. Okay. And this display, so basically let's say this my display that I've written here, so this has to be a global function. Okay, this has to be a global function. So you have to declare in such a way that all the part of the program can access it. That's how it works. Okay, so what if your display function points to a like a, let's say you are writing your my display this function. So let's say your my display function, the job of this display function is to open a window and draw something by mouse click. So basically you will click the mouse and it will draw something. So what happens in this case basically? So you must ask the system to redraw the window every time, basically, because you are clicking and then putting off your mouse and then putting it again. So every time you have to do the redraw operation. So you basically call every time when you do it, you have to call a function. It's called glut post redisplay. Okay, so with this function basically from the mouse function, so that means here I have written a my display, right? But there can be other functions as well. So let's say this is my display. So there can be also mouse function. So let's say my mouse function or something. Okay, also there can be keyboard also. So let's say my keyboard function. Okay, so what will happen, this glut post redisplay, so you have to do it inside this glut mouse function, because you are telling glut that basically every time I draw it, so basically you reshape the window or redraw the window, and every time when you do it, basically the main loop pick events from the queue and call their handlers. So that means there will be other things also in your code where actually you are trying to do this type of post redisplay operation, and there will be kind of queue like here, and the main basically program handler that will choose from here like a sequential manner or depending on the priority. So that's how it works usually in general. Okay. Okay, so after the glut redisplay func, basically, what else? There can be many other things also, but I'm talking about the skeleton code, so there we won't discuss much here. So there is also one thing you will see. It's called the init. So init basically is nothing. It's just initializes the shaders and set the state. There is nothing special about init. You just call it. Okay, and then basically comes another important thing. This is called the glut main loop. So remember that in the OpenGL first lecture, I was telling you that the way OpenGL code works is not like a sequential programming. It's like event-driven programming. So event-driven programming means basically the code will run forever, like an infinite loop. And if something happens, then only the program will stop or terminate. So the glut main loop that basically does this actually. So it tells glut to start reading and processing events. So this program only exits when the user closes the main window or kills the process. Otherwise, it will remain there forever. Okay. So basically, it calls the display callback over and over. So this display, my display callback. So glut main loop calls this one over and over again. And when if it does like in a continuous manner, it sometimes calls idle in between the calling, because so that it can maintain a specific frame rate. Otherwise, it might be a problematic for the display. So that's how basically it works. Okay, and basically you do like a return 0 or whatever in your code basically. So this is pretty much the skeleton of OpenGL code you will see in most of the OpenGL programming examples. Also, this glut reshape func that I mentioned. Sorry, I didn't mention. So there is also another thing, glut reshape function, because you are trying to reshape the window. So this function you also might see sometimes, glut reshape func. Okay. So that's also kind of like pointed to the function. It sets the reshape callback for the current window. So basically, actually, this will be in the same line of these ones. So my mouse, my callback, and all these things. Okay. So this also sometimes you will see in the main OpenGL code. Okay. So this is pretty much all about the basic structure of an OpenGL code. Okay. So now let's see some of the quickly. We'll see some of the basic syntax of the OpenGL code. Okay, and then I will explain quickly things how it's working. See. Sorry. Okay. Uh, So I have put everything in the slide, so I won't have to explain everything because it's just a programming syntax. But I don't want to waste time on this, but just to quickly go through over these type of things. Okay, so OpenGL data types. There are several types of data types like integer, floating point, and like signed and unsigned. And some of the these are some of the prefixes you will use, like capital G, capital L. So it means that it's from OpenGL, and so these are kind of the pretty much the list. Also, you will see many primitives like points, lines, like line, strip, loop, and all these things. I am not explaining here. You can find all the examples in the slides anyway. So these are some of the examples. I think I was discussing about this. So basically, line means you specify the beginning point and the end point, and basically draws the line. And also the line strip means there is a sequence of lines, and something like this. Also, the function format, it has a specific format. So it starts with GL. So notice that this is small gl, and this one was capital GL in these cases, okay? When the primitives and this type of data types. But here, when you have these OpenGL functions, so it starts with small gl, and then basically the function name, and then basically you have the dimension. Like sometimes you have 3f or 2f, so it's a three-dimensional two-dimension, and then eventually these are the arguments of the functions. Okay, and that's how it usually looks like. In general, you will see for all type of OpenGL functions. Okay, so all OpenGL commands are prefixed by letter GL. We have seen this type of thing. Constants begin with capital GL underscore. So commands may be prefixed. Okay, so it's the number of 2, 3, 4. That means it's the number of arguments, like how many arguments are there. Okay, so these are pretty much the same. I'm not discussing all these things here. So GL glad.h, yes, we have discussed already. Okay, color, you can set the color with RGB components. I've just shown an example of RGB color model. So you can think of the last one as the opacity. So that means if you have a high value, so that will have more transparency. Otherwise, you will have low transparency. So that means here, that means 0.0 means it's R, G, and B. So 0% red, 0.5 means 50% green, and 100% blue, and so on. It's pretty simple. Here also it's 50% green, 0% red and blue, and here I have specified the opacity also 0.3. That's pretty much the same. So you can also use unsigned byte, because here we were using from 0 to 1 range. So that means you see the floating point numbers for the colors. Also, you can do it from 0 to 255 range by unsigned byte. So that means here it's like 127, 255, whatever value you want, you can specify here, and your color model will change accordingly. Okay, so background is specified by GL clear color. So that's special. Okay, so that means here is the blue color. Why? RGB or R and G are 0, and blue is 1, and the opposite is 1. Okay. Colors are floating points. This one I have mentioned, I guess. Okay, so this is the main program that I was talking about. So these ones also I have discussed. Okay, there is nothing. Yes, so this GL vertex command, sometimes you will see that like GL begin constant and GL end commands. We'll see some examples of how to do this anyway. Okay, let me quickly go through this. Okay, so let's see some examples of drawing certain things. So let's say we are trying to draw some points basically. So these draws basically 4 points. So see, I mean, I have used this GL begin and GL end, and basically here is some constant. So this is basically I'm drawing points. So that's why this argument goes like this. And basically you plot like 4 vertices. So from this coordinate, this coordinate, this coordinate, and this coordinate. It's pretty as simple as that. So this one is GL lines. So that means this code will draw 2 lines. So one is, So I mentioned that for the lines you specify the beginning and the end. So this is beginning and end of one line, and this is beginning and end of two lines. Okay, it's a simple one. And this is line loop. So basically it draws a square from like a 0 0 to 1 1 0 1 1, and basically eventually it draws a square. So this is a GL quads. So quads means it's a quadrilateral. So it starts from vertex 0 0 and draws like this. Okay, so how will the display function look like if we want to draw a black quadrilateral like here? So I mean, this is just a code snippet I'm showing here, but we will put it in the display function, right? So let's see how the display function will look like. Let's try to write it. Okay. 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 Let's write it here. So display function means this one I'm talking about, like this my display function. Okay. So let's name it as the same. So we're trying to draw a black quadrilateral. Okay. We're trying to draw a black quadrilateral. Okay. So how the function will look like? So basically, I write my display. Okay. So initially we have to clear the color to the preset value, right? So we'll use GL clear. And then here what we like, so basically we clear the buffer. So that means we clear the buffer which is currently enabled for writing. So what we'll write? So we write GL color buffer bit. Okay, so that clears the buffer. And also if sometimes we want to clear the depth buffer bit. I will explain why do we need this. So GL depth buffer bit. Okay, so what this does is that so this one, this buffer bit indicates that the buffers are currently enabled for writing. So that means buffers are enabled for writing. And this depth buffer, what it does is that it's used to eliminate the hidden geometry. Eliminate the hidden geometry. So what does it mean? That otherwise what happens, sometimes from a previously uninitialized or garbage value from the previous frame, sometimes things get problematic with the current frame. So that's why it's always a good idea to use these type of things to clear the depth buffer bit. So that means you basically eliminate any hidden geometry at all. Otherwise you might not see your rectangle. So your code is correct, and sometimes you see that your rectangle is not visible. So it might happen that this is because of some garbage value from the previous frame that's actually like hiding the geometry in some way. So it's always a good practice to use these type of things. Okay. Okay. So now what to do? So we have to draw a black quadrilateral, right? So that means we have to specify the color. So what will happen? So GL color, so floating point color we are using color 3F. So 0.0F, 0.0F, 0.0. So that means it's a black. Okay. So now we have to draw quadrilateral. So for drawing anything, what I mentioned is that you start with GL begin with something and basically end with GL end. And here we are trying to draw quadrilateral, right? So what will be the constant? GL quads, right? And then in between here, basically you write your vertices. So basically GL vertex, let's use 2i, like 0 0. Let's say another GL vertex 1 0, another GL vertex, let's say 1 1, GL vertex 0 1. That's it. So we are pretty much done with this. And so that means this is written within this block, and here, okay, so we are done. So usually it's in the end, it's always a good idea to flush something. So if you use a single buffer window, then basically you use GL flush, or if you're using a double buffer window, then use glut swap buffer. That's it. And this is your display function. So if you use your display function in the OpenGL code, then it will draw a black quadrilateral without any problem. Okay. Okay. So that's how it usually works. Okay. So sometimes we so this is the okay. The order of the vertices are usually in the counterclockwise order. So whenever you are drawing like a polygon or triangle. Okay. Okay. So now we discuss a little bit of the camera. Okay. So OpenGL camera is an important thing. Let me see what is here. Okay. So when we talk about OpenGL camera, so there is a camera metaphor. Usually it's called the camera metaphor. So it's a virtual camera. You won't see the camera at all, and as if it's taking a photograph of a virtual world or the virtual object. So that's why basically that's how it's usually placed. So it always points to the negative z direction. So that means it will look like something like this. So let's say it's OpenGL camera. So it always points to the negative z direction by default. Okay, negative z direction. So that means, let's say this is your coordinate system. So let's say this is usually, that's how usually we plot it. So x is like this, y is basically vertically up. Usually you see z is vertically up, but for the convenience of showing things, we usually show like this. And this is basically negative z, and this is basically positive z. So my camera is here. So let's say my camera is at the origin, or it can be anywhere. So let's consider that is in the origin. So that means this is my camera, and let's say this is the lens of the camera. So that means the camera is pointing in this direction. So that means it's pointing to the negative z direction. So this can also happen, that this is your x, y, z, and your camera is here. So that's also pointing in negative z direction. But we'll see later that let's say your object is, let's say, okay, so in this case what we are assuming is that here is my object. So that means let's say this is your object. Let's say here this is your object. So then it's okay that the camera is actually taking a photograph. But what if your object is here? Then if you point your camera here, it doesn't work, right? So that means your camera is here, it doesn't work. So that means we have to change the camera position to somewhere else, or not change the position, at least uh, like rotate the camera in such a way actually it points towards this. We'll see how to do this actually. Okay, eventually the object can be anywhere in the scene, and you have to specify your camera position in such a way that it actually points to the object. So it's a very nice with OpenGL that you can manipulate everything. So where exactly in your coordinate system the camera will stay and how it will point like, and you can do it within the function itself. So we'll see how actually this looks like. Okay, so this is basically the what I was talking about. So you can consider this as a kind of bounding box, and this is a camera. Okay. Okay. So projection is something that we'll see later in the like viewing lectures also, but just for the convenience I will show it somewhere here. So this is basically kind of projection means representing the 3D object into the 2D. So that means you have your object, and there are many ways to represent like a 2D format of the same object. Okay, so that means you have here x, y, z, and you are trying to put the z coordinate to 0. So as if imagine that this is your x, y, z coordinate system, and this is a kind of like a plane here, somewhere, let's consider at the origin. So basically, as if you are trying to put these things onto the plane and keep the z coordinate to 0. So then how this will look like? So this is more like a orthographic projection. So orthographic projection means there is no perspective. So that means all the objects will look like the same. So there is no effect of distance. So that's what we usually do with the orthographic projection. You will also see what is called the viewport. So that means it's a rectangular area of the window where actually your drawing will take place. So that means this is a teapot we are trying to draw here at this particular window in the screen. So it won't be visible somewhere here. So that's why we have to specify like the lower left corner. So where it's actually starting, and the height and the width. So it's same as specifying the coordinate of the viewing window. So let's say if you say that this is my xy starting coordinate and this will be my right hand side coordinate and left hand side coordinate. So you don't have to specify individually things like this. So you just specify the beginning or the lower left corner and the height and the width, and rest of the thing will be calculated automatically within the OpenGL. So that's why this GL viewport function that has four like arguments. So lower x, lower y. So that means this x and y, and width and the height, and then eventually you can plot it. Okay. So viewport basically values are of course in window coordinates. So you do it in GLART reshape func. So reshape func I was discussing previously that when you want to redraw your window or reshape your window, so you have to do this viewport thing. So there are lots of examples you will see later. Okay, so this camera metaphor that I was talking about, that you have to imagine that there is a virtual camera that is taking picture of the virtual world. So what happens? The camera has like many things the camera will have to consider. So you have to determine which part of the world will be recorded by the camera. So you cannot capture the whole world, right? I mean, if you're taking a like a digital camera or your like phone camera, you are taking a specific part of the world in your camera. So that means you have to determine which part of the world you are trying to photograph, because you cannot fit the entire world in your screen. And also your computer screen is not too big for fitting the scene of the whole world. So that's why these things are to be handled in the camera metaphor. And you have also have to see how the camera sees the world, because there can be different types of lenses. So some lenses, they have some focusing effect, so you are trying to focus on specific object, and some lenses, they are wide angle. So basically you have to capture like a panoramic picture or something like this. So you have to specify everything within the camera. Okay, so so here is comes one thing. Let me see what is here. Okay, so basically, as I mentioned, that OpenGL must specify the position and orientation of the camera, and also how the camera will be photographing. So there are two types of transformations are usually associated. The first one is called the projection transformation. Okay, so this projection transformation is concerned with how the camera sees the world and like what part of the world the camera will see. And there is another type of transformation. So it's called the model view transformation. So it determines the position and orientation of the camera, and also the position and orientation of the object in the world. You might find these things a little bit abstract at the current moment, because we are not seeing examples. But just get familiar with these terms, and we'll be using these when we do some implementations in the lab. Actually, then actually you will realize that what's actually going on. So just for the current moment, and like get accustomed with the fact that there are two types of transformations associated with OpenGL camera. So first one is the projection transformation, and second one is the model view transformation. So projection transformation is determines like how the camera sees the world, and how which part of the world the camera will see. And the model view transformation is more about the position and orientation of the camera and the objects in the scene. Okay. Okay, so here what I was trying to say is that your world can be anything. It can be like a light years, or it can be a small sheet of paper, or anything. But in your camera coordinate system, everything will has to be mapped to the device coordinate. So that means everything will has to fit in your device. So that means world coordinate numbers are unitless, right? Because it can be meter, kilometer, centimeter, light years, anything. But in our case, basically we have to do everything in the pixel coordinate. Okay. So all this type of transformation, so that means transformation means you are, as I mentioned previously, uh, we have a coordinate system. Let's say this is your world coordinate system where actually you see the object, and this is your device coordinate system, right? And basically you are taking a camera to picture this, and eventually you are trying to put it here, right? So there is a transformation, and not only one transformation. So from world coordinate to other coordinates, and from there to other coordinates, and finally to the device coordinate. So that means there is a transformation associated, right? So this is a transformation. This transformation is involves many coordinate systems in between. So all these transformations are usually handled by some sort of matrices. We'll see in the next topic how to deal with the matrices. So these matrices basically handle all these type of transformations. Okay. So that's why here um, um, that's why here we are seeing this type of matrix. You see that projection transform as a 4 cos 4 matrix. We'll see later, of course. So all these matrix entries, if these are correct, then basically you will have a nice transformation from your world coordinate to the device coordinate. So there is a like support for commonly used transformation that I mentioned. So orthographic and perspective. So orthographic projection, basically I was showing previously. Well, let me draw here, and that will be much clearer to you. So there are two types of transformations. So the first type is like the orthographic transformation. Okay, so in orthographic transformation, what happens? So no perspective correction. No perspective correction. So that means all objects have same size. Okay. So in this case, what happens? So consider that this is a kind of like the viewing volume. So let's consider like this. Okay. So here is your viewpoint. And this is called the viewing volume. So in this case, this is done by this function GL ortho. Okay, and GL ortho, what it takes are as arguments is like this one, the left. So left means like this plane we are talking about. Okay. Oh, sorry, I think not this one. Actually, left means this one, the back one. Okay, so this is actually left, and this one is right, and basically this one, the one I painted in black. So this is near, and this is far, and this is top, and this is bottom. So these are all basically comes as a OpenGL argument for the GL ortho. So let's directly see here. It's much easier. Okay, so this is a orthographic viewing volume. So what happens here, if you place an object, basically it doesn't change its shape or size. So everything looks like the same. But in contrast to this, if you consider this one, so you see that far objects are basically projected to like a far distance, and basically you get this perspective effect. We'll see like how actually this looks like in the later lectures, but just for the time being, like assume that this is done by this function glue perspective. Okay, so this perspective projection actually handles this type of effect where objects have different shapes if they have different distances from the camera. Okay, so this is a general preview. Okay, so GL ortho, GL glue perspective, and GL frustum. So frustum is also like the general viewing volume. So frustum means it's a perspective projection always. So that means there are two types of projections. So first is the orthographic projection, GL ortho, and second is the perspective projection, glue perspective. The third one is GL frustum, but that's also considers perspective projection in general. Okay. Okay, so what happens in every case, basically there is a matrix that is generated and eventually it's multiplied to the OpenGL state. Okay. Um, okay, so recall that the model view transformation. So where we saw the model view transformation, somewhere here. So I mentioned that there is a projection transformation and a model view transformation. So projection transformation is what are, under these transformation is perspective and orthographic. Now we see that the model view transformation. So model view means is the position of the camera and position of the object in the world. Okay. So in the model view transformation, I repeat this here again, the position of the camera and the position of the object here, and it generates a 4x4 matrix. But the problem, I mean, why not use two separate transform matrix, one for the camera and one for the object in the world? That can be much easier, right? Because why do we need to combine everything in one matrix? Because you might think that we have to specify the position of the camera in a separate matrix. That's easier to handle, and specify the position of the object here in the world. So that's much easier to handle. Why to combine everything and then complicate things? So basically, what happens? Try this experiment that your camera or eye and the object are in the same location. So this one is the blue is the object, and this is the camera or your eye or lens or whatever. So that's also in the same object. Can you see the object if they are all in the same location? No, you cannot see the object. So what you have to do is either move the camera away from the origin. So that means we are moving the camera from the origin to -2 location, or move the object from the origin to, let's say, to +2 location. So is there any difference in this case? Because everything is the same. So actually there is no difference. But that's how actually OpenGL is developed. So programmer can think of model view matrix as transforming the view of the models that are being generated. So that's why it's called the model view matrix. So there are other advantages that were used for developing this type of analogy, but usually for since there is no difference, so basically people combine everything together, and it's called this the model view mode. Okay. Okay, so now this glue lookat. Please get things clear, because the glue lookat is one of the most important function for doing most of the OpenGL operations. Okay, so glue lookat is a viewing transformation. Okay, so it creates a viewing matrix from an eye point, a reference point indicating the center of the screen, and an up vector. So you see that here is basically eye position and where the camera is looking and which way is up vector. Okay, so it will be clear from here. Okay, so as if this person is photographing this bunny model, and we are trying to see the bunny model. So how it will look like in the OpenGL program. So glue lookat is the function. I, at, and up, they are the three arguments. So I means where is the viewpoint. So this means here I is here towards the bunny. Okay. Up, at is means where is it pointed. So that means sorry, I is where is the camera, and at is where is this pointed. So that means it's pointing towards the bunny, and up is the up coordinate system, right? So now let's see an example how actually it will look like here. Okay. Let me write it here. That would be better. Okay. So let's consider glue lookat. So what is our function? Glue lookat. It's I, at, up. Okay. So now I have a glue lookat function. Let's say with these things, and okay. So what does it mean? It means that the camera is at -5 on z-axis, Why? Because this is x, y, z. So that means camera is at -5 at z-axis, and it's pointing towards the origin because this is the up, this is I, this is at, and this is up, right? So it's pointing towards the origin, and up 0, 1, 0 means this is the y coordinate is up, right? So then how it will look like if we draw this? So this is our coordinate system. Up is y, y. So this is x, this is minus z. This is a convention we use, right? Okay. So that means camera is at -5 at z-axis. So that means here is my camera. Okay. So this is -5. It's pointing towards the origin. So that means it's pointing here. And this is basically coincident with the y-axis. So that's what this configuration means. Is it clear? Make sure that you understand this correctly because this will be needed in many other applications as well. Let's take another example. Let's say you look at 10, 0, 0, 0, 0, 0, 0, 0, 1. Okay, so what does it mean? Let's draw this coordinate system. So where is the I position? Can anybody say?
On the x-axis.
On the x-axis, and which position?
10.
With 10, okay. 10, 0, 0, okay. And where is at? So where is looking? Where is looking?
Origin.
Okay, so that means it looks at the origin. So here is my object, and this is with vertically
Y-axis. No, Z-axis.
Z-axis. Okay, so that means if this is Z minus Z, and this is Y, and this is X, so how this will look like? So actually, I have drawn the camera actually wrong. It should not be like this. So Z means it will be like this. So that means the camera will actually, let's erase this part. So the camera will be kind of like this, and it's pointing towards like this. Is it correct? Because this is coincident with the z-axis, so that means it's vertically upwards like this, and it's pointing towards the origin, and it's at the x-axis 10, 0, 0. Is it correct?
Yes, sir.
Okay. Yes, actually this is correct. So with these OpenGL glue lookat function, actually there are plenty of things you can do, and this function is extremely important for different types of OpenGL applications. Okay, so this is the glue lookat function that I was talking about. So basically, when you specify a view, basically you have to do many things. So set the viewport, projection transformation, and model view transformation, and everything. But usually, what happens when you do the transformation? So you set the transformation state for the projection mode and model view mode, and back to a default no transform state. Okay, so this is also important. So this is some of the examples. Okay, so this is basically matrix mode GL projection. So it says that it's a projection transformation. Model view means it's a model view transformation. Actually, these things are much better to see in the code directly rather than actually in the theory. But I just mention it just to get so that you can get familiar with everything. So to the default state, to come to the default state, basically you have to do the identity matrix multiplication. So that means when you do the load identity, it will come to the default state. Okay. So, so this is basically one example. Basically, you do the GL projection and then you do load identity. So which is equivalent to a GL orthographic projection. So these are some of the inbuilt functionalities of OpenGL. Okay. So these are examples. I'm not repeating anywhere. Okay, so this is another example if we put everything in a reshape callback. So basically you specify the viewport, you put your matrix mode to projection mode, load the identity vector, and then do the perspective projection. And again, you can do the model view matrix, load the identity, and do like your viewing operations, everything. So this is how a kind of reshape function looks like. This is not a particular example. I'm just showing a general thing, so how it looks like in the reshape function. So yes, transformations are not drawing command, so they are basically kind of state changing command, and basically we multiply a matrix, and that's how it works. Okay, so this model view transformation has three things: so translation, rotation, and scaling. So basically, translation means you have your x coordinate or y coordinate or z coordinate changed. So that means it's just a linear transformation from one point to the another. So rotation means you rotate it by some angle theta, and that's done by this GL rotate f function. Basically, theta is the angle and degree about the axis that you mentioned. So that means here we are rotating about y-axis because this is 1.0 by 30 degrees. Okay, and scaling is just a multiplying by a constant factor. All these things, and the order is important because the orders are not commutable. Okay. Okay, so there is a small thing, this push matrix and pop matrix. So you will see, let me see how many things are remaining because I wanted to finish this OpenGL stuff very quickly. See. Okay, we don't have much things left. So I will quickly discuss about push matrix and pop matrix operation. Okay, so this push matrix and pop matrix, whenever you change the state, you will see this push matrix and pop matrix operation. So push matrix means you push the current matrix onto the stack, and pop matrix means basically you restore the model view state. So you replace the current matrix with the one below of the current one. Okay, let's take an example. Otherwise, these things get very abstract. You might not be able to understand. And this is the last thing we'll see today, and eventually we'll start actual computer graphics theory from the next class. Okay, so let's take an example of GL push matrix. And the GL pop matrix operations. Okay, let's say GL, my first command is GL push matrix. Okay, sorry. So what it does, so it basically creates matrix 1. So that means if this is your stack, this is matrix 1. Okay, so now let's do GL translate. So we do some translation. Okay, we'll translate it, let's say 500. So that means it applies transformation to M1. So apply transformation to M1. So that means this thing will get translated by amount 5 in the x-axis. Okay. Okay. So now let's say we do like a draw square operation. Okay. So what happens? So it draws a square. So it means it draws a square with transformation 500. Okay, so that means if this is my x-axis, after this command, translation command, so this, let's say this was my object. So after transformation, it does come here and eventually draws a square here. Okay, so it draws square. So now if I do GL push matrix, so what it does is, as I mentioned, the GL push matrix basically duplicates the thing on top of matrix 1. So that means it will look like M1 was here, and there will be another M2 matrix. Okay, the same. So now let's say we call GL scale 555. So that means all XYZ all will be scaled by 5 amount. So what happens in this case? scales matrix 2 only. So that means scales M2 only, and don't do anything to matrix 1. So that means M1 no change, M2 scale by 5 amount. Okay. Now if we draw a square, what happens? Draw a square. So that means it draws a square with both transformation 500 and scale 555. Why? Because my object was already here, so the translation was already there. I haven't undone the translation, and also I have scaled it anyway. So that means when we draw the square, it combines everything. So that means this draws a square with both translation 500 and scale 555. So now if we do GL pop matrix, so what happens in pop matrix means M1, M2 was there, M2 is gone. So that means M1 becomes the top now. So now if we draw a square, so what happens in this case? So M2 is gone. M2 was what? M2 was the scaling transformation. So that means there is no scaling at all. So that means now this GL draw will command like a draw square with only translation 500. Eventually we do GL pop matrix. What happens? Stack becomes empty and everything is deleted. So that's how it works. So that means push matrix and pop matrix are extremely important for handling the transformation. So we want to do a transformation, and then we want to combine this transformation with another transformation. And let's say in the next frame, we want to delete one of the transformation and deal with the next one. So to do all these type of things, this GL push matrix and pop matrix operations are extremely important. So that's how actually it works. So that's what we were doing like this here. Okay. So there is nothing special about it. Okay, so finally just one thing. So this is an example. So basically this code basically draws a green arrow in the screen. Okay, nothing else. So if we do translate F, so that means if we are translating let's say by Z, let's say this is the y-axis. So y-axis we are translating by some amount, so it's basically goes somewhere here. So okay, maybe I will explain this in the next class because it's already 11. So by the way, so this will be your last lecture with OpenGL, and sorry. So this will be the last lecture with OpenGL. From the next class, actually, we will start actually learning things, and I will organize some of the lab sessions for small code snippets, and you can practice everything like this. Okay. So see you tomorrow at 9, and we'll start actually learning things from there with the mathematical foundations. Okay. Thank you very much.
Thank you, sir.
Thank you.